Uh, Hello, everyone. Thank you so much for joining today for the AIAA Los Angeles section our meeting. We have a very special event today, a very hot topic. It's emerging technology in aerospace, and also is great impact and also market as well. So first, some simple logistic. Because it's raining here, so obviously we have more people online than folks here, but we should expect a couple more people to walk in. So for folks online, if you want to, and it's encouraged, if you want to speak out and ask questions, you are welcome to click raise hand on Zoom or type it in chat. We'll unmute your mic. But it's better to look at the situation and see if it's maybe better more toward the end. So the presenters, speakers, they can finish their presentation, but it's something you really feel very important. You can see if the speaker feel that's the right time to open up for answering your question. So first of all, we are the AIAA Los Angeles section. Then this event also open to national, so everybody is joining online as well. So if you are a member, welcome back, and don't forget to renew. If you are not a member, that's okay. Still stay with us, and but if you are interested, please ask us and think about joining the AIAA membership. And if you're in LA, you can affiliate with us. You have volunteering opportunity as well. So I'm speaking actually when we were in AIAA Ascend in Las Vegas in July, there were actually a couple of booths actually already a couple of booths there. Actually, I wish D-Wave can be there in the future. They're talking about quantum computing, doing CFD, all different kind of application in aerospace. But D-Wave have a very special place in the aerospace industry. Not only in the early beginning, there's some connection with TRW, but also because the application has been widely adopted, and many USC, Lockheed, Raytheon, the already interested or already have a system with them. So I don't want to delay further. So I will make a very, very, very simple, introduction, and then I'll turn to our speaker, and they'll make a more detailed introduction. And this is very, very exciting event. So first of all, we have a speaker, is Dr. Parfait Achade. He's a co-owner and the Chief Quantum Innovation Officer at Lighthouse DIG and the research affiliate at the MIT Media Lab. So he's going to give a talk after the VP of Quantum Technology Evangelism at D-Wave, Mr. Murray Tam. And actually in the background, we actually have Ms. Susan Davis. She has been helping, for setting this up. She's very modest, and she's behind anytime we need her. So without further ado, so we will turn the mic to the VP of Quantum Technology Evangelism at D-Wave, Mr. Murray Tam.
Thanks, Ken. Thanks. It's a pleasure to be here. So Parfait and I are going to give a little bit of an introduction to ourselves. So Parfait, why don't you introduce yourself here, and then I'll jump in as well.
Thank you. I'm Parfait Achade. I'm a researcher and affiliate in Media Lab, MIT, where we are using quantum computation and AI to explore how can we design like a city of the future. And also I'm co-owner of one startup, American-based company, Lighthouse Disruptive Technology, where I'm the Chief Quantum Innovation Officer. Here, what we do is we use like AI and scalable AI and quantum computer to help company and to keep disrupting their business model with this innovation technology. Thank you.
Thanks, Parfait. And welcome, everyone. It's a pleasure to be here with you all. I realize I'm online here, but I got dressed up. I'm wearing my French cuffs this morning, so I'm feeling ready here for a meeting with everyone. So I appreciate you all taking the time. And for my portion of the introduction, I'm going to be introducing the technology platform itself and its readiness for helping you with really demanding production logistics, where what you're looking for is fast and reliable optimization. And I think that, unless there are folks who are online who are deep quantum computing experts and have been following the space for a decade or more, what you're going to find is that this technology is very ready for use, very sort of like it's very defined, the applications you can immediately make use of it for. And we're going to try to introduce that to you to have a strong sense. And I love the AIAA's mandate, which is to bring technologies to you that can help you in your mission, right? Help you with the objectives that you're trying to accomplish in your businesses and your operations so that you can achieve your goals and do it in the easiest way possible. As the Vice President of Quantum Technology Evangelism, my role is to help global businesses and organizations to understand quantum computing and the transformational impact it can have for them today. And I've been with D-Wave, I just celebrated my 23rd anniversary. So I've been in the space a long time. I'm going to try to focus on core things for you to know, but feel free to ask questions. I'm happy to answer questions on a variety of topics. Okay, let's jump right in. Why hybrid quantum computing right now? There are a variety of very computationally complex problems that are not getting well served by our classical IT infrastructure. And you can tell because they're the pain points in our organization. You're working on some problem, you'd like to be able to achieve something, but you're finding that your IT systems just can't handle the complexity. You're going to have to break it down and have different teams work on different pieces of it. Or maybe you're able to put it in there, but it just takes too much time to get to a good quality solution. You need responses much more quickly. You have to be responding in an agile fashion, and you just can't wait for the optimization to take place on a classical computer. Or the other thing that is a common problem that we're talking with folks about is that it just consumes too much energy to do these types of computations with classical computing systems. And the notion here with Quantum Realized is that we're able to help you identify a platform that's available to you and where are the places where it can provide impact right now. I'm going to talk to you about that in a general sense to help you identify, how to recognize a problem like this. And then Parfait is going to take you through a specific example in your area, as a subject matter expert. Okay, first things first. If you've never seen a quantum computer before, this is the heart of a quantum computer. This is a plate with a series of electrical boards, and then at the center there's a cover here, a gold cover, underneath which is a silicon chip, which is the quantum computer itself, the QPU, quantum processing unit. This plate is actually about the size of my hand, and the chip underneath is about the size of our thumbnails. So when you think of a quantum computer, it's a computer chip. It's just operating in a specialized environment. It's in a refrigerator that's about the size of one of us. We could hug the refrigerator. And it's in a little room, that's the size of one of our offices or something like that. So that's when you're trying to think of what is this thing I'm interacting with, when I'm programming the system in the cloud, it's one of these. Okay, so I am regularly talking to business leaders around the world who have heard about quantum computing and are trying to get a sense of, how to engage with it. What is it? How do we use it? What is it going to be useful for? And they're finding it challenging. And honestly, it's because a lot of folks in the quantum computing industry make it a lot more complicated than it needs to be. Maybe they're early in their technology readiness level and they're talking to you about how they're building their technology. And that's probably not your core concern. Your core concern is how can I use this to help me accomplish my tasks more effectively? So we created this framework called Quantum Realized with 3 core components to help folks assess quantum computing and the quantum computing providers in the industry. And that's because D-Wave is very different from everyone else who's providing quantum computing systems. This framework will, centers around 3 aspects: performance, reliability, and then commercial use of the technology. So the first is, can a quantum computer outperform classical computers? And we can definitely do that. The second thing, does this have the kind of reliability? Is this a scientific experiment on an optics table in some university lab somewhere? Or is this part of my IT infrastructure? These systems have high reliability, like 99.9% availability and uptime. Our quantum computers have sub-second response times. We've got SOC 2 compliance. So a lot of the features that enterprises are looking for building and maintaining their business software systems. And we also have customers with applications in production. I'm going to talk about a couple of those. Parfait is going to be talking about a very specific tailored example that's, I think, applicable to your industry. But there are businesses who are currently using quantum computing technology in their application workflows and bringing them value. So this is not a research project. This is like software that folks depend on to operate their businesses. Okay. I'm showing you an illustration here, just to orient you. It's a direct comparison between one of the world's largest supercomputers, the Frontier supercomputer, with one of D-Wave's quantum computers, the D-Wave Advantage quantum computer shown below. And we were studying an application problem in magnetic materials to sort of showcase how big of a difference can there be between classical computing and quantum computing. Now, you might be thinking magnetic materials. Okay, I'm not working in that space, but it was chosen specifically because it's a known hard problem that's been well studied before. We know what makes it hard, and we know how that hardness grows. So it's a great test bed to showcase, what the computational requirements are. And in this head-to-head comparison, we were able to show that for one of the world's largest supercomputers to solve this problem would have required as much electricity as the world uses every year. And our quantum computer was able to complete these calculations using less than $1 worth of electricity. That's the magnitude of the difference between classical computing and quantum computing. So knowing that this technology is available, the next obvious question is, okay, well, where are there applications in our businesses and our economy right now? So let's talk about some customer success stories. Now, the two examples I'm going to provide here are not aviation-specific examples, but the problems exist in the aviation industry to highlight on. And between these examples and what Parfait is going to be talking about, you're going to start to get a bit of a sense for how to recognize problems. So Pattison Food Group owns 13 different grocery brands in Western Canada, and we work with them at one of their stores to help them to create the schedules for their at-home grocery delivery drivers. And in the process of creating schedules, we were able to save them 80% of the time to make those schedules. Once they put that application into production in 2022, then they moved to a second application, which was workforce scheduling in stores. And the feature that I think is going to be very relatable, not just in terms of workforces, but also in terms of like aircraft and crews and, like assigning physical resources to tasks here, is that, each of the people had training to do some specific tasks, not all of the tasks. So they were a subset of tasks that they could be assigned to. They could work, at the cash, they could work in the deli, but they didn't know how to work in the floral department or the butcher department, for instance. They also had, time varying demand. Every day of the week and every week of the year, the demand was changing. And then they also had constraints, which are like, if someone works a night shift, they can't work a morning shift the next day. So we helped them solve that problem. They've taken it into their pilot production. They're through their first phase of release, and they're already expecting to save their workforce 50,000 hours every year. So, the assignments of aircraft to particular segments has a very similar flavor to it, which is like, what are the constraints? What are its capacities? What types of legs can it take on? So there's a lot of similarities here and to build on. In this example with Ford Otosan, so here they're faced with a task with their Ford Transit line of like optimizing the production of these vehicles, and they also have a series of constraints. Their objective is they want to even out the intensity of the work all day long. They don't want prolonged periods of very intense work and then prolonged periods of very quiet work. They want to kind of have like an even workload, but they also have constraints in terms of like the sequences with which they can construct larger vehicles versus smaller vehicles, paint colors, which side of the door of the vehicle are the sliding doors going to be on. We were able to help them schedule 1,000 vehicles in 5 minutes when it used to take them 30 minutes. And the quality of solution was better. And this is really important because they're working in an environment that's constantly changing, right? Constant disruption is the new normal. So being able to react and recover from disruptions quickly in 5 minutes rather than 30 allows them to maintain that productivity and efficiency. So the point I want to kind of highlight here is that there are a spectrum of applications for quantum computers. There are some revolutionary, simulating molecules, CFD, for instance, right, that are in the future, those revolutionary applications. But today, we can use D-Wave quantum computers for applications where you are trying to assign resources to tasks, and you have a pool of resources, and all of the decisions you make are interconnected in that scenario. So you have to make a coordinated set of decisions that maximizes your use of all the resources. The way we do that at D-Wave is we build quantum computers themselves. We've made 6 generations of quantum computers. These are the most advanced systems in the world. We provide access through the cloud. So this fits into like an existing IT infrastructure through like a cloud API call. That's where our systems have these really high reliability and availability and uptime. you program these systems in Python. You don't even need to know quantum mechanics to program quantum computers. And we also have teams of folks who can help you with that process. And Parfait has been through this process of like, how do you go through discovery, proof of technology, and then proof of concept to show that there's relevance and you can create solutions here. If you're interested in learning more past this webinar, we've got an event happening in Boca Raton, Florida, January 27th to 28th. That's our Qubits 2026 conference. Parfait is going to be there. He's going to be speaking there. It's a great opportunity to come and meet people and talk to them about how they're building solutions and experiencing the technology. So with that, let me stop my share and hand this over to Parfait. Do we get an AIAA discount? Yeah, that's a good question. Let's start the conversation and see where it goes.
Can I move forward or do I wait for the question?
I think you can go ahead, Parfait.
Okay, perfect. So thank you, Tom, and thank you for having me here also, for Susan, that she's humble, as Ken said, and also for giving us this opportunity from the way of empower this solution that we will show here. Okay. So this slide, I put this slide to highlight somehow quantum computer can help and also can impact in the aeronautic and astronautics field. That is important. So it's like how can we use quantum computer from physical modeling to operational optimization to real world problem, as Tom has said. So we can think a little bit about if in this aeronautics and astronautics field that we have like a physical challenge. Could be about maybe like a dynamic of winds of or some kind of stuff of that. All these challenge are governed somehow with differential equation. So we can map this differential equation straightforward by linear equation, and after that we can use that like a quantum computer, a computation or optimization computation, as Murara said, and we can have some kind of outcome of the challenge that we are talking about. Another way to do it, also that we can do it efficiently, is also find a way to write down some kind of function of energy that we call Hamiltonian. So it's like yes, this dynamic, this physical dynamic, I have the way to map those changes into some kind of Hamiltonian, and I can apply some kind of technique of Hamiltonian simulation, and also at the end try to solve this problem with quantum computer. That means that we already have a framework, and also, as Tom said, we already have the matching to solve some kind of problem now. So from the physical modeling to the operational optimization. So we can do it faster, smarter, and also optimize and operation. Nevertheless, my talk will focus. I wanted only with that slide to show that there's a lot of things that could be done. But today I will focus in the optimization problems that we have done with D-Wave and for Vueling. And I will follow this roadmap, some kind of introduction about the problem that we are trying to solve, the definition of the problem, how we model this problem daily and weekly, and how we model in quantum, and the result, and some kind of discussion to focus the public that there's a lot of things that we can be done now, not in 10 years, okay? And we will have some kind of a conclusion, okay? So let me minimize this. So, and the problem that we were solving, the case that Tom and Susan was helping here with, like how to solve here, is the Vueling. Vueling is an airline company in the Europe, is into the international group that we call EIJ in Europe is related to Iberia group, that they had a headache to solve some kind of problem that is close to scheduling problems and is like at the first stage of disruption problems. That's a very big enough for the airlines company, because this problem of disruption is close to 10% of revenue each year. So this, to solve this problem, Vueling started the planning process like a very far away, like a 3 months, 4 months before the due date, and they start with like the network planning, the profitability, and after that they move to the scheduling problem and also the crew planning, and let us say that weeks or days before the due date, they focus in the tactical problem and about the short-term planning. Okay, but actually, the biggest problem that they had is that these processes are very manually, so they didn't have it. They didn't have it. They didn't automatize this problem. So if the problem is manually, the optimality is not guaranteed. That is one of the headache that they have. The process is slow. Not all the requirements that they need are met, and only smallest modification are performed. Okay, and the goal by solving the goal of this project is very clear. That is, how can we maximize the aircraft utilization, but by minimizing the flag rescheduling respect to the original network. That means if our solution, even if it's very good enough and is very far away from the actual solution, doesn't make sense to them. They cannot apply them because they cannot change all the plane, they cannot change all the crew, they cannot do that. So the actual solution have to be very close to the original network. So the benefits expected was like let us make it, let us move from manual to automatic. Make it flexible, and also let us find some friendly flight pattern to operate, to help the department operation to move forward, and also to have like for the whole company like the profit increase. So for the definition of the problem that we are trying to solve is an NP hard problem, to be technical, but this problem is called network adjustment problem. That is about optimizing like airline flight network by aligning the schedule and the resources subject to operational need and the regulatory need. At the end of the day, what we are saying is we have like some kind of black box. When we have the schedule and planning, we have the fleet assessment, we have the maintenance, we have all this stuff, but we have also this restriction that is operational restriction, commercial and regulatory restriction. Okay, at the end we will have the optimal network, but one important thing here is about the objective function that we have to design. We need to take account the number of the variable, because in the era that we are now, D-Wave has one of the fastest quantum computers, and but is not infinite numbers of variables. So if we want to use the QPU, we are talking about the 5K a qubit. That is a lot. But when we are talking about hybrid, we will see we are talking about 500,000 variable, or like 100 millions and possibility of regulated. But this, we need to understand how to map these problems. So we need to take account also in the definition of the problem that we are trying to solve all this information. So as we didn't have a lot of qubits, we have a lot, but we didn't have infinite qubit. So we need some kind of key strategy to reduce the complexity of the problem that we are solving. So that means instead of solving the problem by individual flight, where we can have also individual base like an airport, and we have also scheduled things that means we will need a lot of variable to make sure that we have this. We can define some kind of variable that we call sub-rotation, where is like you have this block with the information of the flight, the information of the schedule, and the base airport. That is the airport. That is the beginning and the end airport. And here we can have some another airport in between. This it will be our objective decision object to model our problems. Even if we can model it by another way, but we will face maybe that we have like a lot of variables, a lot of stuff that to solve this problem. Okay, as we have said, this is another example that this is a sub-rotation where we have Amsterdam, like at the beginning and the end airport, and we have some kind of airport here at the end. So as we say that we are going from the original network, so the main input is that original network where we have the regular flight with their initial and departure and the arrival time. We have the base airport, and we have the subfleet. Subfleet, we call subfleet the type of the airplane. So this is some kind of example of our objective function. So the original network look like this. So the colors is the kind of subfleet, the kind of airplane that they have. And here we can see the base, and we can see the initial departure and the arrival, and the whole sequence of aircraft that is performed each day is called the rotation, and the sub-rotation that we define like our unit of cooperating is this one. Okay. So this is the starting point of our model, but to inform our model to have like a degree of changes on also cancellation of the network, what we first do, we add like optional flight into the network. And this optional flight in the network have the ability to absorb some cancellation or some changes from the network. But the things that we have here is that those optional flight can be scheduled or not. But the original flight that we need are mandatory to be in the network, in the outcome of that we are looking for. And then having this, what we do also in the development is how can we generate all the sub-rotation before using the quantum computation. So we have the generation of all the sub-rotation applying the retiming, that means the capability of changing this schedule, the fleet change, that the capability of changing the plane, and the base change that we can change also the base, the initial and the end airport base. And also we design all this sub-rotation to make sure that we have like the turnaround time between all the sub-rotation that can help us to make sure that the plane can take off or not take off when we are designing the schedule. And to think a little bit about mathematics part, but the idea is not dive deeply here. So we have some kind of set of the original sub-rotation. We have also the set of the optimal rotation, that the optimal are not mandatory, and the original are mandatory because they already publish a schedule that the company has. So we need to find the candidate of this sub-rotation that copy the original word and modify the time of the times, fleet, and the base of the airport. This is the main idea. And how can we do that? We use the variable, the binary variable, to select each candidate of this sub-rotation. And also, by seeing this clearly, we also need to think about the restriction, because one good information that we need to inform the model is, yes, perfect. before operate from each base, each airport, we need to make sure that the number of the aircraft that we have here is not less than the outgoing flight and also the incoming flight. That is important. So we need some kind of balance equation to make sure that we cannot use aircraft that we didn't have in the base. That is one of the restrictions that we use. At the end of the day, we have some kind of model that is like a quad symbol where we are maximizing the flight time. Why? Because this is a low cost company. So when they have the flight in the air, very good information from them, and subject to this balance constraint between the incoming and the outgoing craft, and also make sure that all the original flight must be scheduled once, and the optimal could be scheduled or not scheduled in this part. So having the daily problems, the thing that we need to see now is about the operational limitation. So we already modeled this, but we need to think about the limitation, the restriction about the airport. So the flight cannot depart or arrive in some when the airport is closed or not. So we need to inform the model also for that. Also, we need to inform the model about the early departure and also the late arrival. So we need to restrict the number of departure from this interval. And also from some company and airline company, they have some kind of slot that the number of flight that they have to take off and to land have to be exact, have to fit. If they don't do that, they can lose this contract. So in the model, also we need to inform that each interval, an exact number of flight must arrive or must take off. And the end of time, also we need to see about the overlapping between the flights. So at the end of the day, what we do is we generate the subrepresentation given the original network and the flight, the optional flight, and also about the operational constraints we feed to the model, and the number of the aircraft per base and the subfleet we feed to the model. And here in this case, what we have done, we did it classically and also quantumly by using the wave solver to make a benchmark to see how far are we or not about this technology, and also having like the optimal schedule. And also, as we were saying, that is a very important having a very good strategy by solving this problem. The daily optimization process is split into divide and conquer. So the first step is let us maximize the flight time. Let us make that the coverage of a business is fit. And the second time is let us minimize the retiming. Let us minimize the impact of the rescheduling already published flight. That will help the operational department to do not change a lot of flight, or to do not change a lot of crew, and also the maintenance stuff. Okay, so seeing this, there's another problem that we need to face. So it's the synchronization of the weekly problems. But because as we model this project, we model them by facing the daily solution. But we need to synchronize also some flight that during the week have to take off the same hour. So this information also is important. For that, we need like a larger time horizon to relate of this variable, and from that we have like a new variable image to compute this time where each synchronized flight is scheduled. So we define all this, and at the end of the day we saw that, wow, this problem could not be solved classically we need to solve it quantumly, but we didn't have all the qubits that we need. So we need to find some kind of a strategy to do it and to make sure that we can solve them in very short time. So the strategy is given by this slide, where we have like a step 0. So daily optimization, we have the daily optimization. We do the sync feasibility, the mass flight time, and the end we solve the retirement. But to say something here, when we solve one state, we embed this solution, we inform this solution to the following state to make sure that our model can have all this lexicography that we want and face the solution. And now, as we are using the wave, because we are annealing, and to be honest, now the quantum gate base cannot solve this problem because we are talking about 200 qubits, but this problem we are talking about like a 2,000 qubit, 4,000 qubit, and so on. And if we are talking about like a hybrid solver, we can talk about 500,000 variables. So, and this problem, we need to focus in the wave. And this is the reason that we were doing with the wave this proof of concept. And the framework that the wave has is very straightforward, as Tom has shown. They will have like a two biggest framework. That one is about the QUBO, that is the quadratic unconstrained binary optimization. That is the modeling, the MILP, the mix modeling, the classical modeling that you have. If you want to use QUBO, that is unconstrained, and here we have constraints. The thing that we need to do is we need to convert these constraints into the penalty function. This is the way to do it. So having this constraint that we have here, that the flight have to be mandatory here, this is the conversion of the penalty function. So if we want to go through the QUBO modeling, we need to remap all these constraints, because QUBO is unconstrained. But the wave has another framework that is CQM, that is constraint quadratic modeling, that you can take your classical modelation and you can embed directly to the quantum computer. And they have some kind of tools that help you to adjust all this mapping stuff. So you don't need to know how to deal with this penalty function if you want to use the CQM. And also we will see that the accuracy or the effectiveness of the model is very, 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 very good. So the result that we have achieved, and by using D-Wave and by doing this strategy and modeling here, we can see here that we add like a 258 new flight, close to 6% of new flight, and we have optimized like 4% of the network. And by doing the retiming, the first step of the retiming and the second step of retiming, we made like 94% of efficient. That means the solution that we have in the first stage of the retiming, we have like a lot of bunch of solution that the model gave. But the problem here is the company cannot change the already published flight. So they need like yes, let's change. So the second step of the retiming gave like a very good solution for them. And the solution look like something like this, where you have the new flight in this blue color, you have the synchronized flight, and you have all these ongoing development. Okay, and the thing that we can discuss here, like or we can show up like a result, is about the modelation. We test the model in like a 6 scenario, and we can test a more scenario. So we move from 100 variable to 2K variable, and we will see the table that it was good. We compare these two framework that the wave has, that is about the BQM, that binary quadratic modeling Kubo, and the CQM, that is control and quadratic modeling. And we saw how they work and how they handle higher the structure of the complexity. Okay, and the solution that we have got here, comparing benchmarking with the classical solver, we have seen that all these problems are solved in less than between 5 and 10 seconds to solve that. And this time is very good for the company, and also to face the disruption stuff. And like a strategic conclusion of what we can say, that the potential of the scalability of this hybrid computation, quantum computation, of solving this real world optimization problem is in this sector is very, very clear, and very, let us say that is very close to us. Okay, here we can see some kind of benchmark about the scenario that we have. By one hand, we have the hybrid solver BQM, and the other hand we have the CQM, and we can see that. And in the case of BQM, we have like in all these sets, we have like three state that they did the optimal solution as they want, like a retiming. The model fit the optimal solution, but the solution, like the retiming that they wanted, didn't fit like easily on that. But with the CQM, in all the case, they fit the good solution. And also compared to the classical part, there's some scenario that the DWF solver let us say that beat the classical solver here. So what we can say that yes, this solver both evaluate the problem, even if the block time and the retiming problems. And for also to projecting a little bit, we can say that we are capable to use like 500,000 binary variable from the DWF problem solvers or computers. 100 million quadratic iteration, that is a lot, and like 100K explicit constraint. That is a lot for the problem that we can solve now. And we saw that the CQM had a greater expressiveness than Kubo. Why? Because with the CQM, you don't need to design the penalty function. So you can embed directly the model that you are doing. So by defining the penalty function, because Kubo is unconstrained, this also can be the cause that CQM is good enough for that. So we have seen that we hire competitive in 5 seconds, and some others in 20 seconds, that maintain the high quality of the variable. And we saw that the potential of this complex solver of what we are talking about. With this, we are working in some kind of paper where we show that we can use like a quantum computer, in this case Avantage 2 from D-Wave, by solving NP-hard, very NP-hard problem, because this problem is not only one NP-hard problem, is the combination of a lot of NP-hard problems that can be solved with hybrid quantum computer. It's like Tom have said, this is very good news. We don't need to wait a lot of time to solve these combinatorial optimization problems. Okay, and the way hybrid computation is already capable to address this real-world problem, as Tom already said. And here I'm showing the platform that we design is modular, is extensible. That means could be adaptable by taking account these technology. And here we can see that yes, if we want to compare to gate-based approach, they still need like they require further development for the immediate use is is not realistic because of the number of qubits that is limited, and also because of the decoriance that they are there. They are there. And the wave here has this computer that can be that useful nowadays. And nonetheless, as we also focus in the innovation stuff, we are still working in that part. And if some question here, I will be very glad to answer some if you judge it necessary.
Great, Parfait. That's fantastic. You know, one thing that kind of came to mind. So while you're thinking through some questions here, typing some questions into the Q&A or through the chat. Oh, Ken, do you have any questions just off the top?
I personally have question, but we first want to ask people here and also online. And as a people, Emilio, you have a question?
Yeah, I have a question. I am completely new in this field of quantum computing, especially applied to flight operations. But my question is, since I am neophyte about quantum computing, how do you define the number of qubits that you need to assign to a given variable in this flight operations function?
Yes. No, Tom, go ahead. Go ahead, Tom.
So, okay, so one way to think about it is, well, probably the first thing I would want to kind of highlight here is that if you look through Parfait's demonstration, there's a series of places where he said, like, hey, here's a real world constraint, just expressed in the English language. And then Parfait is like, I know how to express that in math. And then the tools allow me to express that in software. And then the solver can take that in and then help us coordinate our decision making, taking that into account. So let's just say, as an entry place, if you can just describe your problem in the English language, you're done. Because Parfait can take it the rest of the way and build a solution for you and allow you to evaluate, to assess your return on investment. If you're thinking about, when that happens, the core piece is to try to make the relationship between what you know about your problem and your description of the problem and the way that it's implemented with mathematics, you want to make that as close as possible. The math should be like a direct relationship. And so if you're basically making a decision of like, okay, am I going to switch aircraft here? Then you're going to assign a variable to that decision. Everywhere in your business scenario where you're like, okay, I have business decisions to make, there's basically a variable that matches that. And the next thing I want to highlight here is that classical computers have some tremendous strengths that we can leverage, and quantum computers have some tremendous strengths. It would be possible to put every aspect of this into the quantum computer, but we would need such a large quantum computer, we wouldn't be able to take advantage of it right now. So let's use the classical computers to drain everything that they find easy. And then let's use the quantum computer for helping us move through the solution space in the ways that classical computers struggle with. So in many cases, we're using a classical computer to ingest the whole problem and then to begin to make local changes in the decisions. And then that algorithm will make a call to the quantum computer and say, help me rearrange some section of it and maybe suggest some like much larger redistribution, or like several decisions are going to change at once to help me move through this space more quickly and more effectively. And that's how the quantum computer is getting called. So it's not even necessarily the case that you're taking the problem and fitting it into the processor. It's more like the classical algorithm is making use of the processor to help it move through the solution space. I'm hoping that isn't too abstract. Is that?
No, I understand. Now, in a practical case like this one, used by Rueling, the Spanish airline, then they don't have in their headquarters, let's put it in a simple way, they don't have a quantum computer located there in Barcelona. They just transfer the information of the decisions that they want to make to Parfait. And he said, okay, guys, give me your problems and I will develop a solution here in MIT. And I send it back to you what you have to change in your flight operation, in your day-to-day flight operation.
Yeah, so let me define a structure, an example structure. So you have all of your existing IT infrastructure. I don't know if you're using SAP or some other enterprise level software to manage your business data. That tells you about your current state. When you describe your problem to Parfait, he's going to write an application code with, like open source tools that basically solves it. But that can actually exist within your IT infrastructure where your data is. And it'll make calls to that system and say, what's the current status? It'll have a model for what are the factors to take into account, and then it'll make queries about the current state of your flights and then pull those together. And then it's saying, okay, now I have a network of decisions with relationships that I need to make. And then it can separate out the decisions from the labels. So like at that point, I just have a set of integer, binary, and continuous variables to set. And the labels of like, well, this is a flight going from this location to that location, stay on the business side. And then a cloud call can get made. And then that calls the platform, which starts deploying classical and quantum computers to help us. It sets the variables. And then when it hands that back to the IT system on the customer side, it takes the solution, puts it back with the business data. And then it says, oh, okay, this variable is telling me I need to change flight 463 and flight 621. And that exists in that business's IT infrastructure. So that's how that interface kind of works. And so it's sort of like a cloud platform that you're making remote calls to. And what Parfait is building is something that kind of can exist on the customer side for making those queries.
So there is a daily interaction between Parfait and the airline. In this case, it's a day-to-day interaction between them, because Parfait, is the one who handles the quantum computer side of this decision-making program.
I mean, yeah, let Parfait take that.
Yes, yes, I understand a little bit what you're saying, and Tom gave like a very clue stuff here. What Parfait is doing is only defining the model. Once Parfait defines the model, Parfait disappears. Okay, and we have a model, and this model, if the business side will have some kind of the dashboard and also the input variables about the flight and something like that. When they change something like that, they are changing. We call the model, and the model will be executed in the D-Wave computer, and we gather the information, the result, and we show back to the business decisions makers. So is that. So here the thing that we are doing is like a perfect. The business department want to make some kind of decision. They want to play with some kind of a flight, change this, and see if by doing this iteration they can maximize or not their revenue. Okay, so they do that, but what we built is like a black box that collect this information, this iteration,
Yes.
model them in the Kubo on CQM, send this to be computed in the D-Wave computers, and take back the result. This will be the production, but now we are not in the production. We are in POC, proof of the concept. But at the end, this will be the roadmap and the way that they can use this platform.
Okay, so in the future, we expect to have, for example, a quantum computer, or each airline can have their own quantum computer, so they cannot.
No. It's like now. Let us see the way that a company has stored their let us say data they didn't have at home. They have in Amazon, AWS, they have in Azure, they have in Google. So like D-Wave, I guess I'm talking about D-Wave, but D-Wave will fix me. D-Wave, we have like a cloud-based business that you when you want to send like some kind of petition, you will send it to his cloud, and it will be a pay per use or pay per whatever that they will decide to do that. So you will have your application, and when you want to solve some kind of problem, you will send it in the cloud of D-Wave, and by solving this, you will pay only pay per use or pay per whatever Tom and Susan decide to model their business value proposition.
Understand. Thank you. Thank you much. I yield because I'm using too much time.
Yeah, and just to clarify, we do have customers who actually have acquired whole systems for research purposes, for defense applications, for because they're building up levels of effort. But for the types of applications we're talking about here, it's much easier to start. You can absolutely begin where you're seeing return on investment from the initial project and moving on from there. So cloud access allows you to kind of like access just what you need for the application, and then you're basically paying a cloud subscription for the application that you're running. And then I see Albert Musa has asked, I see a set of two equations you're solving, but can you clarify the difference between the two solution methods in terms of how each is handling the variables and the constraints? So Parfait, you touched on this a little bit, the QBO and the CQM. You're still on mute there, Parfait.
And can you repeat the question? I didn't follow.
He said, I see the set of equations you are using, you are solving, but can you clarify the difference in the two solution methods in terms of how each is handling the variables and the constraints? Okay.
No, totally. So it's like the first part that we solve, we translate is Tom. This was your first answer to the gentleman in the room, that what we do is, yes, taking this requirement and the problem that they are solving, we transform this to some kind of integer, let us say that in simplest and classical modeling, and like integer modeling. And when you have this in the Kubo formulation, before going to the Kubo, what you have, you need to define your objective function, but you also need to take in account all the restriction that you have, because there's a lot of restriction that you have, or maybe they are binary or not binary. But in the case of the Kubo, what you need to do is, as Kubo by definition is unconstrained, you need to write down this restriction into the objective function. And the tool that we have to do this is called penalty function. So you need to convert this penalty function directly to this constraint to penalty function and embed them in the objective function. This is Kubo. But for the CQM, you don't need to do any of that. You take your objective function, you take your restriction, and you embed directly into the D-Wave solver, because they already work on some kind of framework that can absorb a classical modeling.
Thanks, Parfait.
Can I just follow up on that?
Sure, go for
Maybe
it.
all right. Okay, I heard you, but would that solution apply for any set of equation, or is it tailored for this particular case?
Which solution we are talking about the BQM and CQM?
I presume you said you put it into your qubit, whatever you called it, and then you get the answer without having to work through, because you already have a framework that handles the solution with the constraints and the penalties. Okay.
Totally.
All right. I heard that, and I could visualize a formulation that does exactly that. The question is that specific to this set of basically linear problem, or is it you have to change it to have a different solution for another differential equation problem, for example?
Good question. And No, this framework is general, is generic. So the BQM and CQM are generic. So you don't need to do that. Only you need to know about the framework that if you are using CQM, you don't need to work about the penalty function. And if you have this, you can use it. This is generic. The only thing, and also we are talking about quadratic, not linear. That is very good. So the modeling that they are giving us, the way is giving us here is about the quadratical, is constraint quadratic modeling. So it's not linear. That is like you are going there. But this is the short answer for you. And D-Wave solve all this and find some kind of, if we want to go deeper, like a technical stuff, so there's something that is called like a Lagrange multiplier, okay? So D-Wave calculate this Lagrange multiplier efficiently for you. But in the case that you don't want D-Wave to do that, and you have this capability to modify this factor, you can do it by yourself also.
One of the points I'll just add here is that, Albert, is that all of these mathematical expressions are universal in the sense that you could trade between them. It's just that however closely they match your problem, that can reduce the overhead when you're creating the program, and as a result, the solver can do a better job solving it. So our quantum computers natively solve an unconstrained formulation. If you have a large unconstrained formulation, then use the QUBO solver, and it's very closely related to the QPU. However, like in the example that Parfait was giving, if you have constraints, and many industrial optimization problems include constraints and also continuous variables, then a CQM solver formulation allows you to more naturally express that. So it's less work for the programmer, it's less work for the solver, and it helps you get better quality solutions. So it's just a choice you make by just evaluating how closely it matches. And then I also saw a question from Sean about, how this relates to MRO activities, maintenance, repair, and overhaul. And we didn't get a chance to talk about that. We probably don't have much time because I know we're getting to the end here, but that is an application space in terms of coordinating MRO activities. GE Vernova has actually done some interesting work on like maintaining a variety of distributed vehicles and how do you get asset sustainment coordinated effectively that way. So that's a really interesting problem as well.
Can I just follow up on that? I'm still struggling with what's so different in the two. There is, but it's not coming to my understanding. Let me just draw an analogy between CPUs and GPUs. And the reason GPUs are doing so much better now is that you're solving several equations simultaneously instead of linearly. Are you doing something similar?
Let me jump here. Yeah. Look, to understand, this is technical, and to understand a little bit what D-Wave is doing, you need to go back to understand a little bit about quantum mechanics, but not quantum mechanics hardly. But let us understand this. There's two principles, but we focus only one in quantum computer that is called superposition. Okay, so what D-Wave is doing is, yes, perfect. I have like this initialization. I have like a bunch of initialization. Classically, as the model that we have to solve, to compute is sequentially. So we solve this, after this, after this, after this, after this. By using the superposition principle, D-Wave can take all these, let us say that, all these scenario and put them in superposition and find out the optimal state that can give out the best solution. And this is what it's doing. And D-Wave is doing this with the QPU. But what Tom said is also, yes, perfect. But classical computer are doing very well about like optimization stuff, about like maybe about some kind of stuff that. So let us use classical computation to do those stuff that they have a very strength things here, and where they are weak about like executing several things in once. Let us use the quantum computer to do that. By combining this capability, they create like the hybrid solver. So with the hybrid solver, what they are doing is, yes, they use the quantum tunneling and quantum annealing to make some kind of superposition of all the possible solution. Instead of going through one sequentially, they go by doing tunneling and all together by using superposition. And they are using the classical part by finding the fattest part. This is the way that they are using by solving this QPU and CPU problem. And it's working.
Thanks, Parfait. And Ken, there's a question from Robert. Do you have any more time, or should we?
Yeah, welcome. You can continue.
Okay, so Robert asked the question, I heard in your presentation, have been told often need about 1,000 qubits before quantum would be viable at the AIAA conference, a word lecture to have acceptable reliability and functionality for aerospace optimization problems. Clearly, D-Wave is above the threshold now with max capabilities. On what order is the cost for first implementation to use the order of 1,000 qubits? And how fast is that cost decreasing given qubits available or at least doubling every year? Is there a significant difference in cost based on how much of your problem requires delegation between the quantum compute portion of the problem and the traditional compute, example, switching costs, latency time? So let me just to mention the hybrid part, and then Parfait, I think maybe you can comment on like how people should think about the resource effort when they're doing like an initial, like a solution. So if they were like working with Lighthouse DIG and basically saying, hey, I've got a new problem, I want you to kind of like go through initial implementation to show me what the return on investment would be. So, so Robert, I'm sort of answering the second part first, which is that when I first started talking with customers about our quantum computers, they had to program the machine instruction. And then we got all the way to the point where we created an open source framework for hybridizing classical and quantum computers, at which point our customers' reaction was, hey, that's great that you've hybridized it, but I don't really want to be an expert in how the workload gets divided. I just want to solve my problem. And so that's why we ended up creating these hybrid solvers in the cloud. So the discussion is not so much about how many qubits have you got, and as that changes and the workload changes, how is the charge structure going to change? That would make this a very complicated conversation. Instead, what we're basically structuring is, let's define a problem and a solution that uses this platform, and then define a subscription for that application that gives it a strong return on investment. That's basically the viability. What is the return on investment for your organization? How can we create the subscription cost so that you get a strong return on investment there? And then at that point, D-Wave is maintaining and constantly developing this hybrid infrastructure. So it's in our best interest to push as much work onto the quantum computer as we possibly can, and to get you better solutions in less time. And that in that way, this platform that you're working on just gets more performant and more reliable over time. And we're focused on maximizing the impact of the technology and creating the solution. So you don't have to worry necessarily about those details, but that's a good conversation to have. And then Parfait, you know, the question that Robert's asking is, I think, a question on a lot of people's minds, which is, how much effort is it to go from, hey, I have a problem that's a pain point that you feel is a close connection to quantum computers, to, okay, well, here's a proof of concept that allows you to evaluate how well it does on your data and the return on investment you can get in your business.
And depend of the case, that is very the shortest is depend of the case, and also depend of the company. Because if you want to, you don't want to have like you want to avoid like a Kodak effect or Nokia effect, and your business strategy needs to embed or to adopt some kind of disruption technology. You need to explore all that, and therefore technically, I think that is not big effort, because D-Wave didn't design their framework like an ocean for PhD people. Not. You don't need to understand quantum mechanics to solve these problems. Not. It's not like that. And if you have seen my talk, you will see that like 80% or 70% of the talk was like how can I model the problem classically? And after like 2 slides or 3 slides was how can I move this to quantum? So technically the effort is not too much, but you need to know how to model stuff. and and how to use also D-Wave by solving the problems. I think that D-Wave have a lot of tutorial and they have a lot of material, and this, if you are technical and you have a technical, it's straightforward. Or not, you can have company like Lighthouse that are let us say that engineering, and that can be helpful here. And how it costs depend of the problem, like we are talking about, the like this solution that you see it from boiling. We did it in 6 months, from the beginning at the end, 6 months. And 6 months not full time stuff. So it's like 6 months. You starting by assessment, you starting understanding the problem that they have, you understand all this stuff, and you understand this, you make some kind of presentation, you make sure that you understood all, and you make this, the proof of concept that we have done, it was 2 months. 2 months.
There you go.
2 months.
I mean, which is, yeah, I mean, it's kind of like, if it's a brand new net new application, you know, think about it like scoping the cost of it. Like, well, what's a small team of people going to cost for 6 months to develop a new application? That's very comparable to what any new application requires to build. And then as Parfait was mentioning, if it's an example, if you've seen an example from some of these other business examples that are very close to a problem you're solving, the chances are it can happen more quickly because like a lot of the mathematics has been previously worked out. So we've got a question, which is the optimization used by Vueling actually being used for the day-to-day flight or other airlines? I'll mention that for the Pattison Food Group example and the Ford Otosan example, those are being used on a day-to-day basis. So they're regularly calling our systems to create those solutions. Parfait, what's the answer on the Vueling side?
The question is, if
is it being used for day-to-day flight, like by Vueling right now?
And yes, the way that we test is not in production yet. There is not a production, because this is one thing that in the closed future we need to talk with D-Wave to see how to make this production. But the test like a lot of a scenario, and they have seen that they can reduce a lot of solutions. So they test it during 3 months. That because we have some kind of license by D-Wave. And during this test, we were seeing, they saw that this is yes, they want to push this in production. So this test was like a real test. So the benchmark, the way that they are using it, like now, without. In the beginning of my talk, I said that they were doing everything manually, and now they have some kind of process how to solve this, and they saw that there's a lot of flight that they can be fixed, and this makes sense to them. So I think that as this is the POC, and the next step will be like the user interface, and talk with D-Wave and see how can put this in production. But it's like a closely using it. Okay.
Right on.
Edward has a question.
I'm sitting back here. I might not be in the video, but I was wondering, do you ever have any challenges with decoherence when it comes to superpositioning a lot of different data constraints, or is that mitigated by the organization classical?
Oh. Okay, I get what you're saying. And this is actually kind of related to the question that Albert's asked about why is it called quantum computing. So maybe I'll kind of stitch these together. So the reality of quantum computing, all we need to know is that effectively it's become energy efficient compute for hard problems. But the vision for it is to use quantum effects to perform calculations that are too slow or too hard to do with classical computers. Now, humans, we generally have a hard time really understanding what quantum effects are, but to a computer, it just looks like a resource. So what kind of a resource does quantum mechanics represent? So it turns out there's multiple ways to use it, and each of the ways sort of has a different model description of it. D-Wave, we're building two. So for all the examples we're describing right now, we're using the annealing model of quantum computing, where it's using quantum effects to allow the computer to move between solutions more quickly. And so if we're creating let's say a schedule like Parfait was talking about, let's say we start with a schedule, we're not happy with it. We want the computer to move to a better schedule. And then from that one, better still. And then from that one, better still. We want that process to happen as quickly as possible. The speed limit for quantum mechanics is faster than it is for classical mechanics. So, and we've been able to show that and prove that and provide evidence of that in research papers. So that's the idea there. And in gate model, the idea is to allow the computer to store more information. And that turns out to not be as good for optimization, but to be very good for molecular simulation or differential equations. So things like computational fluid dynamics. So that's a second set of applications. The trick is that those systems are just a little bit early in their technology readiness. And we're probably about 7 to 15 years away before we're going to be at a level with gate model. And I'm talking about the whole field, not just D-Wave, before we're going to be able to impact commercial applications. So that's in the realm of revolutionary applications that are important, that are kind of out in the future for us. But these applications and optimization are happening right now. Now, that's the context setting. The question was, how do you handle decoherence, which is a type of error that you get in quantum mechanical systems? So if a quantum mechanical system can explore multiple solutions at once in constant space, meaning in the same amount of memory, decoherence basically collapses that and it starts behaving classically. So the interesting thing with quantum mechanics is that it's famously delicate, famous for collapse. Think about a coffee mug, right? Coffee mug is hot, right? And because it's hot, it's giving off energy. It's evaporating liquid and all the hot molecules are leaving and leaving a colder thing that's left behind. Even if I put that in space, if it was a complete vacuum, that would happen. It would shed energy, heat away from it. In quantum computation, if you're making a calculation where part of your calculation happens in an excited space, then when it releases energy, it drops out of your computation and that causes an error. That's a decoherence effect. The thing about quantum annealing is we've flipped it. So the quantum state that you're doing the calculations in is the low energy state. So what happens is that if a photon comes in and decoheres your system, it has to excite. But then it naturally can just release that energy and collapse back into the quantum state and then continue with your calculation. So that's why people often talk about fault tolerance in quantum computing. And usually they're talking about gate model, where you have to actually design an error correction scheme to make it fault tolerant. But the interesting thing about quantum annealing is that it's naturally fault tolerant. The machines are fault tolerant by design. So in a sense that like if you get decoherence as you're looking through solution spaces, it basically collapses you on a schedule. And if you just hold it there, it'll actually go back into an exploratory phase and continue looking through for better solutions. Sorry, I got into some technical weeds there, but I hope that was a fun question and answer. And I just see one last question from John, which was, have the D-Wave quantum computers been used to analyze data with sensors such as gas spectroscopy and other direct sensor applications? Not like in a quantum sensing type of application, but more in like if the sensing levels for like some particular liquid level are used as an input to decision making about how do we coordinate the production of a set of liquid products or something like that, then yeah, it can be called as an input. But in that sense, it's not the quantum computer that's interacting with it. It's more like your business system is like keeping track of a set of sensors, getting data on the current state of its operations, and then calling the quantum computer to like optimize, the next things that you're going to be doing based off of that. So I hope, John, that kind of answers your question.
John, you have the mic. If you want to elaborate, or that's good enough. No, John has a mic. Well, if he doesn't, John, do you want to say something more? Well, maybe he's satisfied. Okay, so this is last question. All right, so this is really wonderful, and really thank you so much. This is amazing, and as you can see in the chat, as Susan mentioned, if you are interested in going to Qubit 2006, you know, D-Web can consider a discount for you, so you can contact, you know, and also mention about this picture in the picture of qubit or 4400 qubit for the chip, you know, D-Web just showed. So it's really amazing. I think this is a great discussion. We encourage discussion, and you can see more and more application of quantum computing in aerospace. And also the technology itself is also developing very rapidly. So all right, so let's thank the speaker again, Marie, Parfait, and Susan in the background. So thank you so much.
Ken.
Thank you. And look for the next one.
Thank you.
Thank you so
Thank
Bye,
you
much.
so
Parfait.
much.
Bye, Murray.
Thanks,
Bye-bye.
Parfait.
Thank you. Thank you. Bye-bye. Bye-bye.
Bye.
We start the recording.